function on 0 to 1. Yeah, sure, right? T to the n is continuous on 0 to 1, right?
Yeah.
And so here, I think maybe drawing a picture is what maybe that's what we're missing here. So here's 0 to 1, right? And let's see here, n equals to 1, here's the graph, right? N equals to 2, here's the graph, right? N equals to 3, here's the graph. All right? So fine. I mean, each n definitely gives us a function which is continuous on 0 to 1. Right?
But not for varying t.
What's that?
It's not for varying t. You have to choose a particular fixed t.
For fixed t?
Like,
Well, I'm
If you not make t big enough.
well, I'm graphing t versus say y equals t to the n here, you know. So we're okay. So is it also clear that this sequence? Excuse me. Let me say it this way: xn is an element of C01. I think that's also clear, right? It is indeed a sequence, right? This is a sequence in the closed and bounded set C01. I mean, it's not even C01. Excuse me. It's right in here. That's what I'm talking about. It's in there, right? And I think he just puts the bar over the, I don't know, guys like this or that. I'm not, you know. So, do we agree that for each n, it's continuous, right? The linear, the quadratic, the cubic. And it's closed, right? It's closed because we're how is this? I'm sorry, how is this closed? How is that closed?
The ball is 0 1.
Oh, my bad. So what does ball 0, 1 mean here? Let me be careful. So it's yeah, it's f from 0 to 1, right? Let's say to the reals such that the max on 0 to 1 of f of x well, that's the norm, right?
Yeah.
And that norm is less than, so minus 0, but that's, good grief. I guess I could put minus 0 here, there, just to be dumb. So that less than 1, right? So it's something I don't understand, because if we're talking about continuous functions on 0 to 1, right? It doesn't, I don't think they're in there.
Is it because it doesn't converge pointwise?
Well, I'm not even convinced that I'm not even convinced the sequence is in there, because unless I'm misreading something, f of 1 is 1. I mean, xn of 1 is 1, right? And So,
It's closed ball. So it's
Yep.
less or equal to 1, right?
oh, less than or equal to 1. Oh, thank you. Thank you.
Are you talking about?
I'm a dummy. That bar matters, doesn't it? Okay, thank you. Okay, okay.
Yes.
Okay, so then these are in there. And then what?
Well,
I'm using T.
There's no subsequence. You can't take parts. You can't take some of these items and increasing collection of ends that also stays in things.
Well, what's confusing to me, guys, is like, I don't see, I'm having trouble seeing that it's, if it's closed, right, then the limit of the sequence, curses, I can't even put words.
Because it means that.
Yeah, what's the limit of the what is xn going to?
Well, it's going to go to 0 if it's, well, unless it's 1. It's not uniformly convergent then. Is that part of the point? Because if t is strictly less than 1, the limit goes to 0, but if t is 1, then the limit goes to 1. Right? But that's not,
Yeah, I mean, that's the thing is I see that it pointwise converges to this function, right? That's like what xn, you know, goes to this red discontinuous function pointwise.
oh, yeah.
But we're not doing pointwise convergence, right? We're talking about convergence in the.
Subsequences, yeah.
We're talking about we're also talking about convergence in the uniform convergence norm, right?
Right.
So.
Well, what it covers.
So I mean I know I mean it's definitely it's a closed set because of the construction, right? And we just proved, like earlier in this class, that any sequence in a closed set will converge to a point inside the closed set. But what is the point that it's converging to, this sequence? That's what I'm having trouble processing at the moment. I mean, whatever it converges to, let me say xn, let me say tn, curses, no, xn. So we want xn, the norm of xn, you know, minus, let's call it x star, right? Which is what? That's the max for t, let's say an element of 0, 1. Norm of t to the n, right? Minus whatever this function is, x star of t, right? That has to be equal to 0, allegedly. I mean, that has to go to 0, rather. Unless I'm not tracking some definition here correctly, you know? But the trouble I'm having conceptually is I don't understand what x star is. Like, what is the limiting function for this sequence of functions? I mean, it's supposed to be a function which is continuous, right? Does it have to be? I think it has to be continuous. The whole context of the world we're living in here is continuous functions on 0 to 1, right? And we're in like a subset of that. So, sorry to leave you guys hanging here, but this is where we got to today. It's annoying, isn't it? So let me just tell you where we're going. Try to put a smiley face on it here. So next up we have, this is like the standard example of a infinite dimensional space where you have a set which is closed and bounded but not compact. That's the point here. So in other words, Was it?
You talk to me?
Oh, I thought you said something.
I just called, sorry.
Oh, it's okay. So, compact implies closed and bounded. That's a generality of normed linear spaces. The converse direction, though, right, that closed and bounded implies compact, that's not generally true in infinite dimensions. This being an example of it that we don't quite understand, right? So sorry about that. I did look at this a couple days ago, and I just, for whatever reason, I'm something, not in the technical sense, but I'm dense about this. I don't know, Anyway, so up next we have Ries's lemma, which further characterizes like what we can do in a normed linear space. And then theorem 1.3.34 is the, basically what I keep saying here, but here it is in explicitly. A normed space E is finite dimensional if and only if the closed unit ball is compact. So allegedly we're going to show here the closed unit ball in this space is not compact. And then the proof of that again touches on some of the same technology we used last time to prove the equivalence of the norms. That's kind of cool. And so hopefully I will get through the end of section 1.3 next time rather quickly, and then we'll be full bore into Banach spaces is my intention. So sorry we got hung up on this one, but that's the name of the game in here sometimes. Any questions, Audric?
No, I've just been trying to think about it. Like, I was like, well, if you assume it's, I don't know, like, when you wrote the max thing, I was kind of like, well, does it actually equal 0? Or does that go to, it goes to 0, but as it then goes to infinity, so it's like uniformly converging, right? But, I don't know, you can take like a function like that equals like a constant function of 0, and that's continuous for all x less than 1. But if you take like, if f is equal to 0, you can't have a sequence of xn that goes to 0 as well.
Yeah, if I put 0 here, then this is always 1.
Yeah, so
yeah.
Like, maybe that's, I don't know. That was the only thing I could think of. Is like, oh, well, now you have two sequences that don't converge the same thing.
Yeah, that's
like
fine.
I have an f that's...
It wouldn't converge uniformly.
Yeah, there's something I'm missing here, and I'm going to try to figure it out before next class, so we'll see what happens.
There's a theorem related to pointwise convergence and convergence of subsequences.
Well, we learned last time like that there is no norm that will reproduce pointwise convergence, right? So Audric, I think I'm going to hold off starting the Lie algebras until I'm like done with GR, for the sake of not going crazy.
Okay.
If that's okay with you.
Tomorrow or today.
And then I was thinking maybe let me stop recording this. I was thinking